Hello and welcome to this presentation related to remainder theorem. This is actually part 2 of the lecture. In the previous presentation on remainder theorem, we outlined the underpinning theory that's derived from polynomial division, some basic terminology, and we used remainder theorem to find the remainders associated with quadratic and cubic expressions and equations. It's preferable to review the previous presentation before reviewing the contents of this presentation. Here's an overview of the presentation. We'll commence with a very brief recap of remainder theorem associated with quadratics and cubics, and we will solve further questions related to remainder theorem. This is essentially a continuation of the problems we covered in the previous presentation. Again, helps with recap of applying the remainder theorem. Then we have example 1s. We're going to use remainder theorem here to generate two simultaneous equations. In example 1s, we will solve the equations using a direct solution. And example 2s, again we're going to generate two simultaneous equations using remainder theorem, and the solution of these simultaneous equations is just slightly more complicated in example 2s. And this presentation does assume you are familiar with the generation and the solving of simultaneous equations using the elimination method. And the presentation concludes with some tutorial questions for you to attempt at your own pace related to the solutions of example 1s and 2s. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are rounded to the nearest minute. And for your reference, there is a separate presentation related to the solution of simultaneous equations using the elimination method as outlined on the slide here. Some basic terminology. This is recap from the previous presentation. A polynomial expression is that of the form ax squared plus bx plus c, that's a quadratic, and within remainder theorem that's termed the dividend. The numerator here is a dividend. A linear expression, for example of the form x minus p, that's termed the divisor within remainder theorem, that's a denominator in this case. So we'll be using the terms dividend and divisors throughout the presentation. Here's an overview of remainder theorem applied to quadratic equations. As I said in the previous presentation, we show the underpinning theory of how remainder theorem is derived. And here's an overview of remainder theorem. This is applied to quadratic equations, quadratic expressions. The underpinning theory of this theorem is outlined in the previous presentation. Here we're just going to state the theorem. So if we have a dividend of the form ax squared plus bx plus c, which is divided by our linear expression, x minus p, that's the divisor. The remainder can be shown to be of the form ap squared plus bp plus c. In other words, when you compare the dividend with the remainder, they're both quadratic formats, but the dividend is actually a function of x, ax squared plus bx plus c, and the remainder is a function of p, ap squared plus bp plus c. So essentially the remainder is found by substituting the value of p for x in the dividend. And to find the value of p, we equate the divisor to 0 and solve. So above the divisor is x minus p, so equate it to 0 and solve x is equal to p. So essentially you note a change of sign between the divisor, which is a negative p, and the positive p that will be used in remainder theorem. We will outline the application of remainder theorem to solve quadratics on the following slide. So this is recap from the previous presentation. Example 1q, we're asked to find the remainder. This will be using remainder theorem given a dividend, 2x squared minus 3x plus 6, and our divisor x plus 2. So given the dividend and divisor, using remainder theorem, we're going to insert p for x in the dividend, and notice that p is negative 2 as we have a positive 2 in the divisor. All we do now is put the value of negative 2 in remainder theorem, so it becomes 2p squared, that's 2 multiplied by negative 2 squared, minus 3p, minus 3 multiplied by negative 2 plus 6. Evaluating, we find the remainder is 20. And recap of question 2q, again we're given the dividend, shown here, our divisor, x minus 1 in this case. So we're going to show that the remainder is 0. So as before, using remainder theorem, insert p for x in the dividend, noting that p now is positive 1, x minus 1 for our divisor, so p essentially changed the sign, so p is positive 1 here, and we simply insert the positive 1 in our dividend of 4x squared plus x minus 5. Evaluating, we find the remainder is indeed 0. So in the previous presentation, that now found a factor of the quadratic equation from which we could state that the root was positive 1. Let's consider remainder theorem for cubic equations, cubic expressions. As before, given a dividend, this time in cubic format, divisor, x minus p as before, it can be shown that the remainder is of the form ap cubed plus bp squared plus cp plus d. So we know that the remainder is in the cubic format, as is the dividend. So as for quadratic solutions, to find the remainder of a cubic, we substitute the value of p for x in the dividend. So again, the dividend here is a function of x, and the remainder is a function of p. And we find the value of p in exactly the same way we did for quadratics. Here's example 1c from the previous presentation. We're using remainder theorem to find the remainder of, given our dividend, the cubic expression, our divisor, x plus 1. So as for quadratics, using remainder theorem, we insert p for x in the dividend. Note in this case p is equal to negative 1. So inserting p into our remainder theorem, we insert negative 1 wherever we have an x in our dividend, so it's 3 multiplied by negative 1 cubed, and 2 multiplied by negative 1 squared, minus 1 multiplied by negative 1, plus our 4. And that evaluates to a remainder of 4. Same approach is applied to example 2c. I'll let you review this solution at your own pace. So here are some further tutorial questions related to remainder theorem. So this is essentially a recap of the previous presentation and the application of remainder theorem. I'll let you attempt these at your own pace. Questions 1f to 4f shown here. We have a dividend, divisor, the answers, so the remainder is shown on the right hand side in the square brackets. Just note question 4f is actually a quartic, but you can apply the same principles to solving the quartic as you did for solving the quadratics and cubics. I'll let you think about solution to question 4f. And for your reference, here are the solutions to question 1f and question 2f. I'll let you review these solutions at your own pace. And solution to question 3f and question 4f. Here are further tutorial questions related to remainder theorem. I'll let you produce your own solutions to questions 5f, 6f and 7f. Answers are shown in the brackets on the right hand side. Let's now consider example 1s. When ax cubed minus 14x squared minus d is divided by x minus 3, we're told the remainder is 0. Also, when the dividend of ax cubed minus 14x squared minus d is divided by x plus 2, the remainder is also 0. In this question, we've got to determine the values of a and d. I'll show you the full work solution to example 1s on the following slide. So here's example 1s. The full work solution commences on this slide. So essentially what we're going to do here is, given a dividend and our first divisor, and knowing that the remainder of this sum is 0, we're going to apply remainder theorem and generate an equation in terms of the unknown a and d. So part 1 here, we know from the question the remainder is 0. We divide the dividend by x minus 3. We're going to apply remainder theorem, so we insert p for x in the dividend. Noted that p is positive 3. So here's our function of p, remainder theorem. So 0 on the left hand side, you now insert 3 where we have an x in the dividend. The next line I simply evaluated the cube and the squared terms. And finally I've rearranged the terms into this equation shown here, labelled as equation 1, noting that a and d are the unknowns. We have two unknowns in one equation. We cannot solve this. We need to generate a second equation, and we can do that because of the information in the question. For the second equation, we have the same dividend, but we're going to divide it now by x plus 2. For example 1s, solution continued. This is part 2. Now our remainder still 0, stated in the question. Here's our dividend, as before, with a and d unknown, but now our divisor is x plus 2. And to apply remainder theorem, again insert the value of p or x in our dividend. Notice the value of p is negative 2, so So a function of p here, remainder theorem, we simply insert -2 where I have an x in our dividend. And again, evaluating and rearranging, we generate equation 2, again the same two unknowns of a and d. So now we've got two equations, we can now solve them simultaneously. So example 1s, solution continued. So step 3, as I've labelled it here, now we're going to solve the equations. So here's equation 1 from our previous slide, here's equation 2. We can solve this by elimination. Notice the coefficient of d, both 1. We don't write the ones, but there is actually a 1 in front of the d in both equations, so the coefficient of the d terms are the same. So we simply subtract the equations, that will eliminate d from the equation. So 126 minus 56 is 70, 27a minus a negative 8a, that becomes 27a plus 8a, so that's 35a. And we can rearrange to find a is 2. All we do now is back substitute the value of a into any of the equations. I've chosen equation 2, but you can use any equation you like. So substituting 2 into equation 2 and rearranging for d. d is negative 72. So to summarise, a is 2, b is negative 72. So now we can write the dividend, as shown here. It's 2x cubed minus 14x squared minus a negative 72. So it's plus 72 effectively. Example 1s, solution continued. Just going to show you here that you can check the answers to ensure they're correct. We now have our dividend, it's 2x cubed minus 14x squared plus 72. So inserting the value of p into our remainder theorem, so that's 2 multiplied by 3 cubed minus 14 multiplied by 3 squared plus 72. That evaluates to 0, which is what we're informed in the question, and likewise inserting -2 into the remainder theorem, again we get 0 for our remainder. So we check the answers from our simultaneous equation solution are correct. Example 2s, given a dividend here of ax cubed minus x squared plus cx minus 1. Initially we divide it by x minus 1, so divisor, and we inform the remainder is 3. And if we divide the same dividend by x minus 2, the remainder is 23. In this case we've got to determine the coefficients of a and c. So again we're going to generate two equations as in example 1s and solve them using simultaneous equations. It's just that the simultaneous equation approach is slightly more complicated in this particular instance. Based on the solution of example 1s, if you think you can attempt example 2s without further assistance, I would encourage you to stop the presentation and do so, but the full work solution is shown on the following slide. So here's example 2s, commencement of the solution, part 1. I'm going to let you review this at your own pace. It's very similar to example 1s. Generate our first equation, knowing 3 is the remainder. When we divide the dividend given in the question by x minus 1, apply your remainder theorem, insert p or x in the dividend. Know that p is equal to positive 1 this time, so our remainder theorem, function of p, putting the p into the equation, we can form equation 1. I'll let you look at the number crunching here. Example 2, solution continued, this is part 2. Now we're given that the remainder is 23 when we divide the dividend by x minus 2. Just know that p is now positive 2. So inserting the value of 2 in our remainder theorem, that produces equation 2, labelled here. And example 2, solution continued, here's step 3. We're now going to solve the equation. This is equation 1, equation 2. But notice this time, no coefficients are the same. As from our previous work on simultaneous equations, using the elimination process, we need to factor the coefficients of either the a term or the c term to be the same. In this case I'm factoring equation 1 by 8, so 5 times 8 is 40, equals to 8a plus 8c. Equation 2 is unchanged. And we simply subtract the equations. This will eliminate a, so 40 minus 28 is 12, 8a minus 8a is 0, and 8c minus 2c is 6c. That evaluates c to be 2, and then back substitute the value of c into equation 1 shown above. Here's c inserted into equation 1 above. We evaluate a to be 3. So in this case a is equal to 3, c is equal to 2. So we can now form our dividend. it's 3x cubed minus x squared plus 2x minus 1. Example 2s, solution continued, and again if you want to check the values, A and C are correct. Now we have the dividend, we can insert the value of p into the equation, show that the remainder is indeed 3. So when we divide the dividend by x minus 1, we do have 3. And when we divide the dividend by x minus 2, we have 23. That's just for reference. And here are some questions related to remainder theory, within which the solutions require the use of simultaneous equations. Here's question 1s through to question 3s. Answers shown in the square brackets on the right hand side. I would encourage you to stop the presentation and attempt question 1s through to 3s, but you are expected now to develop your own solutions to the problems. And final questions related to remainder theory that involve the use of simultaneous equations. Question 4s, question 5s. Again, the answers are shown in the square brackets on the right hand side. And here's the bibliography used to help generate the presentation, which I hope has been of some use to you, and as always, thank you for viewing.